Suppose an experiment is performed that can have many different outcomes. It could be an experiment as simple as rolling dice or drawing cards from a deck, or something much more elaborate, such as a manufacturing process. To each outcome, we can assign a probability that the outcome will occur. In this jolt, we will learn about the distribution of the probabilities of all outcomes from a sample space, which consists of all possible outcomes. Ultimately, our goal is to be able to make inferences about the behavior of the experiment itself, based on a sample of outcomes, and for that, an understanding of this distribution of probabilities will be essential. To help us to concisely express probabilities, we introduce the concept of a random variable, which is used to represent a numerical outcome of an experiment. By convention, a random variable is denoted by a capital letter, whereas a specific value of a random variable is often denoted using the corresponding lowercase letter. We will see examples of both continuous and discrete random variables. A continuous random variable can be defined on the entire real number line, or some subset thereof, whereas a discrete random variable is defined on a discrete set of outcomes, such as the integers. When a random variable is discrete and its domain is a finite set of outcomes, a probability distribution for the variable is simply a list of all the outcomes and their corresponding probabilities. This can be illustrated with a simple example. Suppose capital X is a random variable whose values are the possible places in a 10-person race, first, second, third, and so on, all the way to 10th. This table lists the probabilities for the 10 possible places in which a runner can finish. Note that the expression P of capital X equals little x is used to refer to the probability that a specific outcome will occur. There are certain probability axioms that a discrete probability distribution must satisfy. All outcomes must be mutually exclusive, only one can occur at a time. Probability must be a non-negative real number between 0 and 1. Finally, the probabilities for all outcomes must sum to 1. If you go back to the preceding example, you can verify for yourself that the sum of all of the listed probabilities is in fact 1. Ideally, we want to be able to describe the result of an experiment using not a distribution of many outcomes, but a single outcome that is, in some sense, most likely. This leads to the notion of the expected value of a random variable, which is also referred to as its mean. It is defined to be a weighted mean of the outcomes, in which the weight associated with each outcome is its probability, as it makes sense that outcomes that are more likely should be assigned more weight. Note that the Greek letter mu is used to denote the expected value, just as it is used to refer to the population mean. As an example of expected value, we consider a raffle. Each ticket costs $5, and there is a $100 grand prize, 2 first prizes of $50 each, and 4 second prizes of $25 each. To find the expected gross winnings, meaning not including the cost of a ticket itself, we can simply multiply the prize amounts by the probability of winning each prize. To compute these probabilities, we use the fact that a total of 200 tickets are sold, so that the probability of each prize is simply the winning tickets of that type divided by the total number of tickets sold. For example, the probability of first prize is 2 over 200, because there are 2 first prizes. Once we add up the products of the prize amounts and their probabilities, we obtain the expected gross winnings of 1.5 or $1.50. However, to obtain the expected net winnings, we must take into account that each ticket costs $5, which must be deducted from the expected gross winnings. Therefore, each ticket holder can expect to, on average, lose $3.50. That is, the raffle is biased against the ticket holder. Once we have the mean of a discrete random variable, we can compute its variance as well. Note that the variance is a weighted average of the squares of the deviations from the mean. In fact, because it is a weighted average for which the probabilities are the weights, like of expected value, we can actually define the variance in terms of expected values. That is, the variance is the difference of the expected value of x squared and the expected value of x squared. Note how in the first term, x is squared before taking the expected value, whereas in the second term, the expected value is taken first and then that is squared. We will now study some specific probability distributions, beginning with a binomial distribution. Suppose that an experiment can only have 2 outcomes, such as a coin flip. One outcome, say heads, is considered success, while the other one, tails, is considered failure. We then perform several such experiments called trials. The outcome of each trial is completely independent of the others. This is true of a coin flip, for example, because the result of one flip does not affect the next flip. Furthermore, suppose we know the probability of success in each experiment, such as the probability of flipping heads being 1/2. Such an experiment, characterized by its independence from other experiments and its known probability of success, is called a Bernoulli trial. There are many different kinds of experiments or processes that can be viewed as Bernoulli trials. A manufacturing process in which one can estimate the probability of producing a defective unit. Taking a multiple choice exam based on random guessing because the probability of a correct answer is known. Checking whether households have internet connections, where historical data can be used to estimate the probability of having one. In all cases, each experiment is independent of the others. The outcome of manufacturing one item, answering one question, or checking for an internet connection has no bearing on the outcome of the next experiment of the same type. Now, suppose we perform n Bernoulli trials and define a random variable capital X to be the number of successes, k, within these n trials. We need to determine the probability of k successes for each k between 0 and n. Because the trials are independent of one another, the joint probability associated with a sequence of n outcomes can be obtained simply by multiplying the n probabilities of the individual outcomes together. Therefore, if we have the first k trials being successes and the remaining n minus k trials being failures, the probability of this sequence of outcomes taking place is p to the kth power, the probability of k successes in a row, each of probability p, times 1 minus p to the n minus k power, the probability of n minus k failures in a row, each of probability 1 minus p, because we can only have success and failure, and these outcomes are mutually exclusive, so the probability of having either success or failure must sum to 1. However, we want the probability of any k of the n trials being successful, not just the first k all in a row. Therefore, we must multiply the preceding probability by the number of ways in which we can choose k out of the n trials to be successful. The number of ways to do this is given by the binomial coefficient, also known as n choose k, due to this interpretation. Putting it all together, we now have a probability that n Bernoulli trials will have exactly k successes, where successes and failures can occur in any order. Furthermore, it can be verified that the sum of all of these probabilities for k equals 0, 1, 2, and so on up to n is equal to 1 as required. This distribution of probabilities, based on outcomes of Bernoulli trials, is called the binomial distribution. For each possible value of a number of successes, k, the probability of k successes is given by the value of this function, which is called the probability mass function. Every discrete random variable has a probability mass function that defines the probability of each outcome in the variable's domain, in this case the integers 0, 1, 2, and so on up to n. Here we can see some examples of a probability mass function for a binomial distribution for various values of its two parameters, the probability of success, p, and a total number of trials, n. From these graphs, we can make the following observations. First, the binomial distribution is symmetric only when there's an equal probability of success and failure, that is, p is equal to 0.5. Second, the graph of a probability mass function has a well-defined peak, which happens to occur at the value of n times p. For example, in the upper left graph, n equals 20 and p equals 0.5. So at n times p equals 10, and sure enough, the graph peaks at 10. Finally, the distribution is skewed to the left toward lower values of k if a probability of success is less than 0.5, and skewed to the right if a probability of success is greater than 0.5. This makes sense because if there is a greater probability of success, then there should be a greater probability of successes too. We can actually obtain explicit formulas for a mean or expected value and standard deviation of a binomial distribution. Intuitively, it makes sense that if we are performing n trials and the probability of success is p, then we can expect that most likely there will be n times p successes, And in fact, that is the expected value of a random variable capital X that follows a binomial distribution. Furthermore, the variance is the number of trials times the probability of success times the probability of failure. And of course, the standard deviation is the square root of that.